All right, so yeah, hey everyone. It's a very cameral meeting. My name's Marcin, I'm the CEO at Reilabs, and I will be talking about Lampe, which is a tool we've been building to formally verify Noir code. And I will sort of tell you more about like the vision behind it, why I think it matters, how it works, what the goals are, and so on. So first of all, the first point I need to make is that formal verification is necessary in this industry. Are you guys familiar with formal verification? Like we just okay, of course. Cool. So yeah, very quickly, we are building protocols that are securing billions of dollars. We are also building protocols that work with some very sensitive data about our users, right? So like you have identity use cases where we are scanning passports, where we are scanning documents, scanning eyeballs. So yeah, very sensitive data, billions of dollars of value locked. And we're doing all of that with extremely open access to everything that we're building. So if you deploy something on-chain, anyone can just come in and throw any garbage at your circuits, any garbage at your contracts, and see what happens, right? And the environment is extremely adversarial. Essentially because it's so open and because the stakes are so huge, you've got North Koreans testing your systems all the time. But this is not specific to ZK. What is specific to ZK is also that the environment that we are using to build those applications is extremely unintuitive, right? So we have field arithmetic. So you got your developers that are used to like using 2's complement to represent numbers. You come in, oh, it's fields now, right? They cannot easily be compared. They overflow in a very weird place. It's a weird system. And we have unconstrained functions, which means half of our code is only used for witness generation, and it's not actually used as a part of the constraint system, which is to say it's not actually checked cryptographically in any way, shape, or form. Whenever you're writing an unconstrained function, you should think about it as I'm writing an example of how this value could be computed, and not this is how this value actually is being computed. So this makes it even more difficult. And one more subtle point that I don't think gets brought up enough is that we can't even see what is going on. If you are writing a smart contract for Solidity, for example, you can always go to Etherscan, you can see what's been called, how it affects the contract state, what's happening, right? Like if you are getting attacked, if you are getting funds drained, you actually know that you are getting funds drained. But for example, in the case of Aztec, which is the main environment for Noir, we know that some private function evolved the private state somehow. What happened? I don't know. I know it's been correct according to the definition given in the Noir file. If that definition is broken, funds could be drained and you will never even know that this is happening. So with that in mind, I think that formal verification is a necessity here. But at the same time, it's very, very difficult to pull off. First of all, even specifying the properties and specifying the invariants of programs is difficult. If you ask like your random developer that you meet that is writing Noir code, if you ask them about like the invariants, there are chances that they don't even know what an invariant is. And even if they know what an invariant is, how do you get them to actually be good at specifying those invariants? And then formally proving that the invariant that you've specified is correct is a whole other can of worms, also very difficult. And the barrier to entry is also very, very high, right? Like usually you have to learn some new tooling or some new language, be it Lean, be it Cog, currently called Rock. Or if you're doing this with SMT, you don't necessarily need to learn a new language, but then you need to learn how to negotiate with the SMT solver such that it actually achieves anything, which is also a very non-trivial amount of knowledge and experience to ingest. And you also often need to understand the theory of language semantics. You need to understand what's going on with how the language is modeled. So all of that, one more thing. The way this is usually done also makes the process very repetitive. So the way the way this is usually approached is we extract from some very low-level representation, usually with like all functions in line. It may even be just the pure constraint system. Then you can show that, okay, maybe it's uniquely constrained, but you cannot tell anything about the nature of the weakness. And the other thing is that if you, for example, if you have a library and you do a formal verification audit for one customer, there is no easy way to translate that work over to another customer. So those are some of the motivations of why Lampe is happening and why it looks the way it looks. And this is what I'd like to say, like, let's make it all easy, right? Lampe exists, boom, it's easy now. This is the truth. The truth is we are going to make it somewhat palatable. It's still not going to be easy. You still have to write lean, or if we have chosen a different proof assistant, you would still have to learn and use that proof assistant. You still have to understand at least a bit the theory of what's going on. But we're aiming to make it at least an investment that can be made with good conscience for a given protocol. So yeah, let's make it bearable. We bring together well-established theory. We are trying to build tools that are somewhat user-friendly, and they do not assume that you have a PhD. If you do, great, but it should be possible, at least in principle, for someone that's new to this space to actually build something. We are working on custom automations that try to hide away as much of the complexity of the specific theory that we are using, so that you can get a model of your Noir code in lean without any extraneous computations that support the computation of Noir program. I will show you specific examples of what that means later on. And one more thing is that, again, going back to the repetitiveness of this work, it takes a village to make this happen. So we are starting from the assumption that proofs should be composable. So if you are a library author in Noir, you should be able to publish your proofs, your theorems, your lemmas, and they should be reusable for the users of your library. So if you create a library for elliptic curve operations, for example, and then I create a library for signatures, and I use your library for elliptic curves, that library optimally would already come equipped with a set of lemmas that say, the library is doing its work correctly. I can then pull it into lean and say, whenever I'm using the Noir function, for example, for point multiplication, I can instead substitute it for a well-formed definition on the lean side of what the library is doing. And the claim here, and sort of the ambitious goal, is that we can gain enough momentum in this like very early stages of Noir that the base libraries actually will be formally verified, and that in this ecosystem uniquely, I think we can push towards like full formal verification of the core libraries. We could make it a sort of like soft requirement, like a community expectation that your libraries get formally verified, that you share your lemmas, that everything is more correct, right? Because again, this also goes to like supply chain attacks, right? Like if I'm the author of elliptic curve multiplication library, and everyone else is using it, what if there's an exploit in that? That probably can propagate very easily to the entire program that uses that library, right? And again, this won't even be detectable because everything is happening on private state with private functions. Everything is so obfuscated that you cannot easily inspect what's happened. So yeah, Lampe is an attempt at solving this for Noir. And as part of that, we've built an extractor that turns Noir code into lean code. And this is happening at the highest possible level, essentially. So the extracted lean code, I will show you later, looks line by line exactly like the Noir code that you've written. You can actually, you can look at the definitions side by side. They are very similar. We are using and abusing Lean's metaprogramming facilities to actually equip Lean with some syntactic sugars that look exactly like Noir. We extract before monomorphization, which means we also model Noir's type system in Lean. And again, this is done so that you can reuse components as much as possible, right? Like if you have a generic function, if you have a function that takes a generic type parameter, you can prove things about the behavior of this function for all type parameters, and then you can compose that with particular instantiations. And then we implement the semantics of Noir, and how we implement those semantics I'm going to explain a bit later, because this is some heavy machinery. Like this brings together a lot of the theory of semantics of programming languages. And then we have some custom automations that make writing this all easier, so that you can, again, you can just get a sort of semantic model without caring that much about how we actually model Noir, the language, how we model execution. So a bit about Lean. I'm sure most of you are already familiar with what that is. But it's a functional programming language, first of all, with Haskell-like syntax. It's actually a better Haskell. Like if you are a Haskeller, you would find Lean a more pleasant version of what you already know. But the type system is expressive enough to encode propositions, to encode logic. And it's user-friendly enough to be widely adopted. I think it's probably the proof assistant that has the most traction right now. It's not the most popular, but the derivative of popularity is the largest, I would say. So there's a huge community of mathematicians that are building libraries of formalized mathematics. There's mathlib. There's also the effort to prove Fermat's last theorem. So great mathematicians are actually, like this is probably the first time in history that mathematicians actually picked up a theorem prover seriously and are actually doing mathematics using a theorem prover. The Ethereum Foundation has an effort to formalize zero-knowledge cryptography. So you can Google the name arclib and it will show up. And that's an effort to essentially formalize IOPs and Sigma protocols, things like that, to make sure that the cryptography is sound. So it's a different layer that what we are talking about, but it's also very useful. There's a wide array of built-in tactics already. So like there are solvers for ring arithmetic, for linear arithmetic, like inequalities, and some general purpose like proof search tactics like SIMP and ASOP. And it's extensible through metaprogramming. And the metaprogramming is actually pleasant. So like if you come from the Coq/Rock world, you will know that metaprogramming is not the most pleasant thing that you could be doing in that particular ecosystem, right? Like you have to learn a completely separate language, or you just have to write it in OCaml. In Lean, you write the metaprogramming in Lean itself, which is much more pleasant, much more streamlined, I would say. And also a great macro system that lets you do things of, okay, I mixed up the ordering of the slides. Anyway, some examples of Lean, right? So like we have a theorem statement like, hey, addition is commutative. We have a basic proof by induction. This is a screenshot from Visual Studio Code. You will see that it gives you this interactive state of like, those are the things that I already know. Those are the things that I still have to prove. And you proceed by writing your proof script until it completes. Here's another example of doing the same with lists. And yeah, going back to the power of Lean's metaprogramming. So on the left-hand side, you have some definitions of like some Noir code that we are using as a demo for this. This is a part of the implementation of the skyscraper hash function. And on the right-hand side, you can see the extracted Lean. And you will notice that it's very similar. Like the number of lines is almost the same. You can recognize the names. Obviously, like things like binary operators get they get their own proper names. You see that there are some additional like type annotations happening, but we do this extraction almost one by one, so that when you are done with the extraction, you can recognize your original Noir program, and that's easier for you to reason about because when you wrote the Noir program, you actually understood what it was doing, right? So this skips this step of, oh, now I have to parse this new representation that is like mangled, compiled, and so on. No, it's very similar to what we've had. Okay, so let's talk also briefly about the theory behind all of this. So first of all, the requirements or the boundaries that we are working within. So first of all, Noir is a Turing-complete language. And this is a contentious statement, so I put an asterisk on it. Is Noir a Turing-complete language? My claim here is, for all intents and purposes, yes. The non-Turing completeness is very unstructured, kind of random, kind of dependent on what the compiler in the current version can and cannot do. So if you are actually modeling the semantics of the language, it makes sense to assume that it is fully Turing complete. And then as the compiler evolves, it gets better, more programs start to compile, you are open to that, right? Noir is, I would say that Noir is designed as a Turing complete language, but then the compiler sometimes fails to actually compile some programs that would use the Turing completeness, which is not dissimilar to like normal programming, right? Like you could argue that no language is Turing complete because you don't have an infinite amount of time to run a program, right? It supports mutable memory with unbounded lifetimes. So at the very beginning of your main function, you can create a mutable variable, you can take a reference to that variable, and then you can pass it through the system happily. It will just exist for the entire program execution logically. Obviously, like there is a poor man's version of garbage collection in Noir, but in principle, you can have unbounded lifetimes on any piece of, on any mutable variable, really. Like there isn't even an operator to heap allocate something. It's just you have a mutable variable. Technically, it's allocated on the heap already. And it's non-deterministic through unconstrained functions. So what that means is you have this special keyword in Noir, unconstrained, which lets you write some function that is not being cryptographically checked. For the purposes of the constraint system, this is just a fresh variable or a bunch of fresh variables. If they are not constrained properly, then you might as well remove that code. Like it's not, it's like it's not there for the purposes of the constraint system. And this is a source of possible catastrophic bugs, right? And this happens even, it used to happen even with some standard library functions. Like for example, if you took a bit decomposition of a field element, you weren't guaranteed that it was like the unique smallest bit decomposition. So you could get a bit string of the correct length, such that when you recovered the field element, it would be the correct field element, but the bit string actually denoted a number larger than the maximal field element, right? This was patched as far as I know, so currently the standard library makes sure to give you the unique smallest binary representation, but it wasn't the case. So even this could really bite you, right? Like imagine if you use this to implement a comparison gadget. So you decompose your numbers into bits and then you do your like binary comparison. It's broken because the binary comparison, because the binary representation is the bigger one, right? And by the way, it's a bug that happened. I think it happened in every single DSL I've looked at. It's like the easiest mistake to make is assuming that binary representations are easily unique. So all of that means we need some really, really big guns from programming language theory to model all of that. So let's talk about a few foundational ideas. First of all, there is what we call big step semantics. So you have a programming language, and in the and you encode propositions of the form. If I'm starting from a given state, let's call it S1, and I run this program in this state, where by state I mean, for example, all of the values that are being held in memory right now. When this program executes, it will terminate and it will end up in a state denoted as S2. And this composes nicely, so you can go through that. Except Noir is non-deterministic. So we need some extension to that, and the extension we've chosen is called omnisemantics. It was introduced by Chorguerot. And you rewrite the big steps, the big step judgment to be, if I'm starting from some state, all possible execution paths of this program will terminate in states that are described by some predicate. So instead of a single state S2, I have a family of states described by a predicate. And then that is usually a bit too difficult to work with normally. So we introduce what is known as Hoare triples. So a Hoare triple PEQ says that if the predicate P holds in the initial state and the program E terminates normally, I'm going to have Q holding in the final state. So this is kind of how you reason about state updates and correct executions. And there's one more twist that we need in this entire story, which is that we also need separation logic. Because we are dealing with mutable memory, Horde triples are usually horrible for that. Because in the pre and post conditions, you have to talk about the entirety of memory. And this doesn't compose very well. So separation logic restricts the language of the predicates P and Q, such that they talk about sort of local views into the memory, and they ensure that the rest of the memory could be anything. And this gives us very good composability, because if I have one program that works on some piece of memory and another program that holds on a completely separate separation logic on a separate piece of memory, I can compose the two and say together they are like both of those judgments also hold. So yeah, let's look at some example proofs. Here we have a reference implementation of some function. Again, this comes from the skyscraper example. And then we prove that it is equivalent to the version that's been extracted from Noir. This is just a quick example. I will show you the actual real code soon. But I just want to draw your attention to the fact that the overhead that you get from using Lampe versus just using Berlin is quite minimal in this example. So you can see that the enter decal that comes from Lampe. Steps and loop invariant, those come from Lampe. Again, we have steps here. And that is all, I think, right? So the rest of this proof script is actually being, it's actually about the core logic of the program, right? Like you see that we have to convince Lin that we are not overflowing the U8 counter, for example, right? Like we have to do a lot of stuff that is purely mathematical in nature, but the overhead of using Lampe itself is quite minimal. Which is the very goal of this exercise. Okay, one last thing. What Lampe doesn't do for you, and again, this is usually people get a lot of misconceptions about you are building a formal verification framework. Cool. So does that mean I can just install it and my programs get secure automatically? That actually happens. But yeah, no, not this time. So first of all, Lampe doesn't verify the implementation of Noir. We are not talking about what the compiler does. We are not talking about the constraints that are being generated. We are not talking about the cryptography behind Noir. None of that is being checked by Lampe. Hopefully it will be checked by some other efforts in the future, but we are just providing means of talking about the surface level programs in Noir and not how they are compiled. Again, does not automate the job of verification away. You still have to write your specifications, and you still have to use Lean to make sure that those specifications are correct. And it does not reason about unconstrained code. Again, that's by design, because from the standpoint of what is actually being cryptographically checked, the unconstrained code doesn't matter. It could not be there, and the constraint system would be exactly the same. So we specifically remove the unconstrained parts. We replace it with a special operator called fresh that just gives you an unconstrained variable that could, in principle, take any value at all, right? And then you use omnisemantics to say that no matter what the value of this variable is, the program is going to behave correctly. And the typical workflow, or the kinds of things that you can do with Lampe is, first of all, you can have a reference implementation of some cryptographic primitive or some piece of your application, and you can prove that what you've done in Noir is equivalent to that implementation. This is particularly important because in Noir you are often optimizing by moving code into unconstrained blocks. So you are not always coding directly, but sometimes you want to optimize something, so you put your code in unconstrained, and then you add the minimal number of constraints that will make it fly, which is a smart solution often, but that smartness comes with a price of now you have to show that this is actually a correct implementation of what you said it was. You can talk about invariants, so you can talk about things that are possible, impossible. This is particularly useful if you are writing Aztec contracts, right? You could say that for example, like I don't know, the size of the pool never drops below 0 or things like that, right? Again, this comes back to the first step, and the last part is a bit subtle, but it comes back to the composability of it all. So you could rewrite your traits to add some required laws to them, and then you say, and then you know that, oh, if my trait implementation satisfies the law that I impose on it, then some other function using that trait is going to be correct. So again, composability all the way down. And then you put it all on CI, so that if you change anything, you know, because the lint stops compiling, because the extracted version changed. So yeah, you are always secure like that. So it's not like an auditing process where you go to an auditor, you pay them an exuberant amount of money, they give you a neat PDF, then you change something and the PDF is essentially garbage at this point, right? With this, like this is actually maintainable. This is something that you actually put on your CI and you work with that. And where do we go from here? First of all, obviously bug fixes, developer experience, more docs. We are starting the formal verification of the standard library right now. So there you will have like your first piece of composability. Whenever you write an application that only depends on standard library, you are free to use those lemmas that we will provide as rewrite rules for your own programs. And then getting your library verified. Like if you are a Noir developer, if you provide some sort of lower level libraries, particularly like at this stage of maturity in the Noir ecosystem, we are getting a lot of foundational libraries being built. This is a great time to start getting them formally verified, so that we can build a very secure basis for the entirety of the ecosystem, and then we can, as it evolves, it actually has a chance to be the most secure ZK ecosystem in existence. So yeah, here's a link to the repository. And I'm going to briefly show you the actual code of like, this is the wrong window. This is the right window. Right, so yeah, this is the Noir. This is maybe this is a bit messy for now. What this does is it implements the skyscraper hash function, and then it uses it to verify a Merkle proof. And there's a few things I want to draw your attention to. First of all, like this is based on a trait called binary hasher. That's just an alias for a 2-argument function that takes two elements and returns an element of any type, because this is generic. Then we have an implementation that is pretty much just how you would implement skyscraper straight from the paper, except you have some hacks, right? Because you always do, right? So, for example, when you are converting to the bits representation, you are like doing this custom for some reason. The reason is to just show off how Lampe works. So yeah, this is where we go with skyscraper. Then we have the struct skyscraper, and we implement a binary hasher of field elements for the skyscraper thing. And then we have a Merkle tree recover procedure that takes an index represented as already in binary. It takes the proof, and it takes the item that is claimed to be in the leaf of the Merkle tree, and then it does what you would do if you were to recover a Merkle proof. We also have a weird assert equality function. The weird assert equality function is just to show off how we work with unconstrained functions. So we have this unconstrained function that just returns its first element, and then we implement equality by getting that witness element, which is unsafe, unconstrained, and then we do this sort of transitive version of equality assert. Again, this is just as means of an example, like you wouldn't normally do that. And then we have the main function, which calculates uses the Merkle tree recover procedure and it uses the weird assert equality to make sure that the root passed is actually equal to the one recovered from the Merkle proof, right? So like from the circuit perspective, it's rather unexciting. Let's look at the extract. So the extracted version, again, very similar to what we just went through, right? Like we have the same functions in the same order. If you focus on any one of them specifically, you could see that, okay, this is the same up to some reorderings, things like that. We have our implementation again. We have this this magic syntax and our trait input that outputs an object that represents a trait implementation, and then we construct this like environment object that contains all of our definitions. So how do you then work with this? We have the spec file, and first of all, you can see that for some of these, we just do theorems that are like rewrites. So we have the this is our OR triple. The LP is the prime number that we are using because Noir can use different prime functions. The environment is what we've just defined, right? So it's an object that holds all of the functions that are defined in the current scope. This is the expression, right? And the expression is a call to the sign 0 function with no generic parameters and the input parameter for any choice of the input parameter, as you can see here. And the post condition is that the output is always going to be the value of the input modulo 2. And again, when we start this, we get this sort of goal. We call the enter deco tactic, which enters the declaration, and we get this proof obligation, right? So we have the same goal, but the expression changed. And then we run our steps tactic, which is sort of the dummy executor. Like it's going to take the obvious steps for you, so you don't have to like actually compose the proof manually. So after the steps tactic, essentially everything about Noir is gone, right? So we started from this, and then we use the steps tactic, which is again like a symbolic interpreter almost for Noir, and we end up with something that is purely about lean, right? And as proof of that, we use the built-in tactic called simple, which will just like search the immense library of theorems that lean provides. It's going to find one and apply it, and it does, right? Goals accomplished. We're done. Goodbye. This is kind of the most bare bones version of it, and most of the file is spent doing things like that, where we just provide rewrite rules, where we say whenever you call this Noir function, this actually corresponds to this other lean function, and of course it gets more involved. But I would like to draw your attention to the fact that most of this has nothing to do with Noir, right? Again, loop inf, that's ours. That's our tactic. Steps is our tactic, and that is pretty much all. Like in this entire block, the rest of it is actually spent convincing Lean that what you've done is correct. So the footprint of using Lampe is pretty minimal, which I'm very happy with because it was one of the design goals. Okay, so one last thing that I wanted to show you, other than the semantic rewrites, is the main theorem that we can prove. And the main theorem here shows the power of using a proof assistant for this kind of work, because we can actually talk about the semantics of this. If you remember, the main function, it took a Merkle proof, it recovered the root from the Merkle proof, it took a tree root, it asserted that the two are equal, and that's what it did, right? But intuitively, what we mean by this operation is that we are actually checking that this element is in the tree at the given index. And if we are using something as powerful as Lean or any other proof assistant, really, we can actually say that under the assumption that the skyscraper function is collision resistant, and if the root comes from a real Merkle tree, I can actually prove this triple. I can say that with an empty precondition, so like I don't need to know anything else. If I call the main function, again, with no generic parameters and some normal parameters, the root of an actual Merkle tree, the proof, which is whatever the item and the index. I can say with certainty that if this function passed, I know that the item is a member of this tree. And again, the Merkle tree structure, this is defined purely in Lean. It has like its own theory of how it's constructed, how it works, and so on. But the thing I want to draw your attention to is I can actually say something about the meaning of my program. It's not just what it did, but also what it means for us, right? So it's not just that it recovered a Merkle proof. That was just means to achieve something else, and the something else was to ascertain that some item is in the Merkle tree. And yeah, I think that is all I wanted to show you. If you have any questions or comments, I would be happy to talk.
Thanks. I have a few questions.
Yeah.
One goes first. Okay. So there you're using the hash functions collision resistance. Are you modeling as like injective?
Yes.
So essentially, because otherwise you would just prove that like this hash that you know one per image, like.
Yes.
Yeah.
Yeah.
So that's like assuming like you put in the reverse.
Yes. To say it even more strongly, like that's blatantly false. Right? Like no hash function is actually injective, and it's something that like I still haven't gotten around to how to actually model this properly. Yeah. It's very annoying, right? Like one idea I have is like maybe we change the post condition to something like either the item is in the tree or I can actually construct and show you constructively but it gets very weird very quickly.
Of course, that's the same assumption to make. I think it's quite standard, but then like, so I'm not sure it's an argument, but then like their thesis is like, oh, what if you could like ZK prove like a formal proof of something, and then like that type of assumption would be annoying, because then what if someone goes and decides like the ZK proof or the formal proof derived by a counting argument that like the hash is not actually can prove anything, so it's kind of annoying. But okay, so second question is, well, I forgot the second question, so I'll go to the third. So third question is like, so I just asked him this about him because like they have the code of Noir thing, but then like they're doing after monomorphization. So the question I have is like, on Noir...
You're going from SSA, right?
For just after monomorph.
Okay.
Yeah, so Noir has this behavior where it will first evaluate the comp time blocks before instantiating the type parameters. So you couldn't, for example, and I think like since you guys modeled this at a high level, I think maybe you guys have stumbled into this.
So macros get resolved before type checking also.
Yeah, exactly.
So this is already macro expanded, but not monomorphized.
Okay, fair enough.
It's a very lucky spot in the entire pipeline.
Yeah, no, because I mean, I think that's a weird decision by them, and like, couldn't get any nor to explain that to me yet. So just since your model is a good no, but okay.
Wait, how else would you do it?
Sorry?
How else would you do it?
I think in Rust, it got first the type parameters are instantiated, and then you evaluate the content blocks, because you can, for example, you can define an array with size equal to a type parameter in a content block. I'm quite sure if you will. So like if you have a type parameter which is like a constant uint,
yeah,
you can't use that constant uint in a content block, because the content block got evaluated beforehand.
I see.
So you can't like define a constant array inside a content block, right?
Yeah,
Yeah, it doesn't.
That is.
Okay, I'm just wondering about that.
Not something that's beaten us.
Cool.
Cool. Anyone else?
Yeah, I was wondering also if, thanks for the talk, it seems very long proof. You have an estimate of how long it takes in this file, if I use code.
Like to compile it?
No, to write the proofs.
It took like, I don't know, like 3 or 4 days to get it all done. It's not horrible, right? Like it's a significant investment, obviously. Also, like that 3 or 4 days was mostly due to bugs in the system, like in tactics in particular, right? Because this was like the first serious thing we've done with the system. So there was a lot of bug fixing back and forth. Yeah. Again, like I would say the investment, like it's there, right? Which is why I said like we are not making it easy. We are making it somewhat palatable. you still have to invest time and effort into doing this. But I think at this point, the investment is economically justified, which I would call a success.
And so what's your hope with this? Like now, obviously the Noir ecosystem is very young,
Yep.
And this is very helpful because this doesn't exist in any other ecosystem I've heard of.
Yeah.
And so what does this mean for the landscape of like Noir projects that are about to come insofar of like the security aspect compared to other chains? So
Yeah.
you see the whole ZK stuff, but this is like the level above.
Yeah, so I mentioned it before, but I think you came in like halfway through. I really hope that we can build an entire ecosystem of verified Noir libraries based on top of this. Because like the way this is structured is, if you create some lemmas, some rewrite rules for your library, then I, as a user of your library, can import those lemmas as well, and I can use them.
Traits bit as well.
Yeah.
Compose anything.
Yeah, exactly. So it composes the same way, like as a library would, which means, yeah, as you said, this is the first time, this is the first ecosystem that we can actually achieve this. We could have an entire ecosystem of formally verified
And
stuff.
do you think this is going to change the way like auditing is done? Because many other protocols, they say we've been audited like 3-4 times, and then they've done a massive upgrade, haven't done another audits, and then that's when the hack happens. Whereas here, I feel like you would be able to not improve at each step of the way that it does
Yep.
what it does.
Absolutely. I imagine the interaction with auditors changing into auditors auditing the invariants that you've proven, right? Because again, formal verification is not a magic bullet. So like if you're writing this specification, you can still do it in a very stupid way. So someone should take a look and say, yes, like those theorems actually say what you think they are saying. But yeah, the auditors would optimally not have to look at the actual source code, which makes it much more resilient to change as well, right? Like if I have my protocol audited currently and I come up with a brilliant optimization, I have this incentive to not actually update my protocol because I would have to pay the auditors again. Whereas with this, if I have auditors looking at my theorem statements and they say, yes, like if those theorems are satisfied, then this protocol, like we understand that this protocol is actually secure given those properties are satisfied. Then if I come up with a brilliant optimization, I just need to redo the proofs myself. The signature from the auditor is still valid, right? Because I haven't changed the properties of the protocol. And I have provably not changed them. Like I have actual thing on my CI saying that like this property is still satisfied.
You can finally prove that the difference between a need and a feature.
Yeah.
Yeah, I think that's really cool.
Yeah, exactly.